Okay, hello. We're going to look at what polar molecules are very quickly. This video is only going to be 5 or 10 minutes maybe. Today's Friday, so there won't be any new videos or any new material over next week since we've been doing a nice job so far, and we're pretty much where we should be from last year. So, polar molecules. First of all, we have to remember that there are really two types of bonds that we've learned so far. Ionic, and an ionic bond, it is between a metal and a non-metal. The other way I can tell whether it's an ionic or a covalent bond is the difference in electronegativity greater than or equal to 1.7? So you had a sheet a couple weeks ago that on the back of it showed you the electronegativities. If you find the difference between them and it's 1.7 or greater, then you know it's an ionic bond. If it's a covalent bond, we're talking about a nonmetal and a nonmetal. If we're talking about the electronegativities, the difference is going to be less than 1.7. And there are two different types of covalent bonds. There's nonpolar, and there are polar bonds. There's also a number that goes with each of these. If it's nonpolar, the difference in electronegativity is 0.4 or less. If it's polar, that means it's greater than 0.4, but less than 1.7. Okay? So, polar, what does it really mean? It has to do with the pull that electrons have on each other. So, for example, if I have two hydrogens, hydrogen has an electronegativity of 1.0, I believe. Since we have two hydrogens here, and they both are essentially the same atom, two of the same atoms, they're going to pull on the electrons equally. One's not going to overrun the other one as far as pulling on the electrons. So this is going to be a non-polar molecule. Now, if I have something like this, hydrogen chloride, chlorine has a very high electronegativity. It's right next to fluorine, right below it. So this is going to have a higher electronegativity than that. So, because of that, the chlorine is going to pull on the electrons more than the hydrogens will, the hydrogen will. So the electrons tend to spend more time around the chlorine. Because of that, we give it a partial negative charge, and that is it's the Greek letter delta, lowercase. You know delta from MCAT, MC delta T. This is just the lower, it's like a D and then a D, kind of same thing. So this is the capital and this is the lowercase. And it has a negative with it. This is D with a plus. And why? Because the electrons are going to spend more time around the chlorine than it will around the hydrogen. Why? Because chlorine has a greater pull. All right, so on the next slide, we're just going to try to figure out if these molecules are polar or nonpolar. So are they polar or nonpolar? All right, this is CH4. CH4 is methane. I've made it here. Now, it's nicer to work with the models. Fortunately, we can't do that. But if you look at this, you can see that no matter which way I turn this, I'm going to get the same shape with the same kinds of atoms spread out equally. Because of that, each of these hydrogen atoms is going to pull on the electron that's attached to the carbon equally. So not one of these hydrogens is going to pull the electrons more than another. So because we have the same kinds of atoms and they have the same pull, this is nonpolar. Nonpolar. One area doesn't pull on the electrons more than another. How about if I substitute a chlorine? Chlorine is very electronegative. It pulls on the electrons much greater than the carbon does. So this bond right here, represented by that stick, this bond represents a polar bond. Because of that, this is a polar bond. I'm going to make this even smaller. That's what we call a polar bond. And this whole molecule is a polar molecule. So now we've got two things going on. I can have a polar bond and a polar molecule like this one is. This actually is a nonpolar bond. And how do I figure that out again? I just find the difference between the electronegativities of the hydrogen and the carbon. In this case, it's less than 0.4. So, since this is a polar molecule, I'm going to show that with a little negative on that side, and the opposite side is going to be slightly positive. Let's go down to this one. I'm going to erase the rest of this so we can concentrate on that. This thing's going to be the end of me. I've got oxygen, O2. Two oxygens. Because I've got two oxygens, they have similar pull on the electrons that they're sharing. Since they have similar pull on the electrons, what do you think? One doesn't pull more than the other, so this is non-polar. So you can kind of think of polar as pulling. How about fluorine, which is F2? Is it going to be polar or non-polar? Well, using the same logic, since we have two atoms that are the same type and therefore have the same pull on electrons, again, this is going to be non-polar. How about this thing? This is kind of like that, except instead of one green, I would have four greens representing four chlorine atoms. All of these are the same. All of them have the same kind of pull on the electrons. Your guess? Non-polar again. Okay. Carbon dioxide. Now, carbon dioxide has two polar bonds. But be careful. Just because a molecule has polar bonds doesn't mean that the whole molecule is polar. Why not? Let me quickly build it for you. Carbon dioxide, carbon is in group 4. Because it's in group 4, it has to have 4 bonds around it. Oxygen is in group 6. Because of that, it only wants 2 more electrons. So oxygen is going to have 2 bonds sharing 2 electrons. Okay, so Here is my carbon dioxide molecule using models. Carbon's represented by black. The oxygens are red. You can see I've got two of the same atoms on opposite sides of the carbon. Because of this, oxygen is going to pull is equal as that oxygen. Because of that, one oxygen isn't going to outpull the other one, it's the same. So, in this case, I've got polar bonds because these oxygens are kind of pulling the electrons away from carbon, but the whole molecule is non-polar because there's equal pull between the two oxygens. All right, last one is water, H2O. Now, if water were shaped like this, you could use that same logic as carbon dioxide to say that water is not polar. However, water does not make that angle. Water makes an angle like that. I'll show you right here. Water, H2O, consists of one oxygen and two hydrogens. So as far as it looks as a model, it's this. And this angle is important because these hydrogens are at an angle and not across from each other, it's going to allow oxygen to have greater pull. Oxygen has greater pull than these hydrogens down here, and because of that, this area up here is slightly negative. The area across from it is slightly positive. Why is oxygen side more negative? Because oxygen has a greater electronegative pull, greater electronegativity, and therefore a greater pull on the electrons. Since we're pulling on electrons, and electrons are negative, we make that side negatively charged. It's not a full charge, it's a partial charge. So water is a polar molecule. And the polar molecule is made of, this polar molecule is made of polar bonds as well. Okay? So that's the lesson for today. We'll recap it on Monday coming back. Keep an eye on the stream though. I'm going to use next week as an opportunity for those people who have not done much on the online portion to make up all your work, which isn't that much. All right? Let's get it done. Thank you.